Hi everyone, I'm Kathy Zip, Associate Editor of Solar Power World, and I'd like to welcome you to today's webinar, The State of the Utility Solar Inverter. I'd also like to take a moment to thank Advanced Energy for sponsoring this webinar. Before we begin, we'll go over just a few house cleaning items. I'd like to mention that this webinar will be available after the presentation on solarpowerworldonline.com, and it will also be emailed to all registrants. We get a lot of questions about that, so you will get a copy of the presentation. Secondly, there will be a question and answer session at the end of all the presentations. We encourage you to participate. It makes for great discussion. You may submit your questions at any time throughout the webinar by typing them into the GoToMeeting panel, which will be on your right. And then lastly, we realize that not everyone who would have liked to attend this webinar could, so we encourage everyone to tweet about key topics and discuss takeaways using the Twitter hashtag #SolarWebinar. So at this time, I'd like to introduce our presenters. Today, we're happy to have Jeff Harrell, Product Manager for Advanced Energy's NX Inverters, and Joe Brotherton, Manager of Technical Services at Swinnerton Renewable Energy. We're thrilled to have both of you here with us today. And Jeff is actually going to be our first presenter. Jeff Harrell serves as Advanced Energy's Product Manager for NX Inverters. He brings 16 years of field applications, engineering, sales, product management, and program leadership experience with early to mid-stage automation technologies at startups and large corporations, including Nortel Networks and Agilent Technologies. Some of Jeff's project experience includes the Fort Collins Fort Z project under the DOE's RDSI program, the Pacific Northwest Smart Grid demo with distributed controls integration, and Department of Defense Targeted Microgrid Controller Solutions. Jeff holds a Bachelor of Science degree in Mechanical Engineering from North Carolina State University. So we're thrilled to have him with us today, and Jeff, you're welcome to go ahead whenever you're ready.
Great. Thank you so much, Kathy. Try and take control of the presentation here. I guess first I'd like to thank the folks at Solar Power World for giving us the opportunity to speak today. The topic I wanted to explore a little bit with everybody on the phone is grid integration challenges and opportunities for photovoltaic inverters. I think that we're at an interesting inflection point with seeing higher penetrations of PV on the network, a lot more PV getting implemented at the distribution network. So the focus, I think, may be shifting in the industry somewhat from a focus entirely on energy harvest, but also being a good citizen on the grid. So from an agenda point of view, I wanted to just first give a brief introduction to Advanced Energy, then segue into a bit of a baseline of where the industry currently is from a grid integration and utility interactive controls point of view by looking at transmission level integration. It's fairly well understood, fairly well regulated, etc. But then shift gears a little bit and look at the distribution side of the equation. There's a lot of opportunities there, but also a lot of challenges that the industry is facing. Also look at a couple of case studies where we've had projects in the field utilizing scheduled power factor control on a distribution network application, as well as LVRT in the distribution network, and then wrap up at the end. So for a brief intro on Advanced Energy, you've got the corporate stats there in front of you, but basically we've been in the business for 30 years with a strong focus in power conversion solutions, founded in 1981 here in Fort Collins. We are NASDAQ listed, and we are diversified, but with a core competency around power conversion solutions. So you see the two business units there at the bottom with both thin films and solar energy. And we do consider ourselves in a leadership position here in North America in a growing inverter market, which we like to think is still continuing to grow pretty significantly here in the States. This is another view of our activities worldwide. Obviously, we've got a very strong presence in the U.S., but also worldwide with manufacturing in China, presence in Canada, spares and service depots in Germany, as well as Taiwan. So a pretty wide presence worldwide. We also offer quite a variety of solutions for both the commercial market as well as the utility market. We have both transformer and transformerless based PV inverters. If you've kept up with Advanced Energy, you'll notice that our branding TX and NX, I'm actually the NX product manager, which is a non-transformer based solutions. And we do take a very much a solutions approach in our offering to the market, with full integrated skid solutions and complementary balance of system solutions as well. And here you see the services that we provide, definitely leveraging 30 years of experience in power conversion solutions and a lot of proven performance in those technologies. And then building on that, we offer a wide variety of services for both extended warranties, preventative maintenance, uptime guarantees, etc., as well as site level services for O&M as well. So with that brief introduction to AE, I wanted to turn the corner and get into the meat of the presentation. So here you have in front of you kind of a quick look at what transmission level PV integration looks like. Typical characteristics are, fairly large plant size, greater than 50 megawatts at a transmission level. Typically, you will see SCADA integrated in pretty much all cases at a system level, going back to the system controller or ISO. And there's definitely a strong focus around overall data and system security. These plants are under critical infrastructure protection or SIP compliance requirements, so definitely a strong focus around cybersecurity and some work going on to further refine exactly what those requirements are from a smart grid point of view. There's typically also an inverter master controller involved, and utilities don't necessarily want to go out and speak with 50, 100, 200 inverters. Maybe they want to speak with a single controller that can handle disaggregating the control functions to the fleet of inverters. And you can even perform closed loop control with some type of a plant controller at that point of common coupling as well. So with this type of approach, you're really seeing a migration towards a conventional power plant type operation. Hierarchical control scheme from the system operator down, definitely looking more like what's happened with the wind industry from a controls point of view, as well as your more conventional power plants. And there's a fairly clear regulatory environment with the oversight from NERC and FERC. But there are still opportunities on the transmission side that we don't want to turn a blind eye towards. Definitely a lot of press around Puerto Rico and the integration challenges there, the opportunity for forecasting to play a role in ramp rate controls, etc. We're starting to see higher DC to AC ratios. That continues to grow given the price of panels continuing to decline and wanting to really optimize the amount of energy harvest that you have with a large plant. Also looking at storage integration for ramp control. And finally, frequency regulation is something that we're looking for some support from solar plants to be able to provide, in high frequency situations, the ability to curtail or cut back and kind of perform that down reg function that's typically extremely expensive with conventional generation. So with that type of transmission level support, there's definitely a common set of UIC or utility interactive control functions that are expected to be provided by today's solar power inverters. Obviously, enabling and disabling is a very basic function, but necessary. The ability to control reactive power, both consumptive and generative, and that's settable as either a power factor set point, which is the relationship of apparent power to active power, or kVAR, which is kind of a direct request for reactive power consumption or generation. Also, the ability for the inverter to control how it ramps up or down during events. So as you see cloud events, and generation goes away, they don't want the inverter to necessarily produce back its nominal power immediately from an overall grid control function. So ramp rate is obviously very important. Restart controls, similarly, extremely important, the ability to delay that reconnect after some type of a grid event, and not everything coming back on all at once, so implementing some randomization. Curtailment is something that we spoke about just a little bit earlier, and the ability to kind of throttle back a plant in the event of an over generation point of view. Also, your frequency and voltage support functions with low voltage ride through, and some of the more advanced functions that are being discussed, like volt bar control, and then a master controller to kind of wrap all that up and bundle it nicely to a single point of control. So that's kind of what we consider to be the minimum ante, if you will, minimum set of grid functions necessary for today's implementations of solar inverters. So now that we've kind of set a bit of a baseline, let's look at distribution level applications. So definitely in the conferences that I've attended, there's a lot more buzz around distribution level connected projects, upwards of 20 megawatts, connected maybe on a dedicated feeder, maybe adjacent to other loads on a feeder. So definitely getting a lot more traction on the distribution side from a permitting and interconnect point of view. But there's a lot of challenges that we're going to be facing as we see greater penetration levels. So if you look at the UL 1741 spec and 1547, it's somewhat in conflict with how things are done on the transmission network, from low voltage ride through, the ability to conduct voltage regulation down in the network. So those things have to be reconciled. I mean, there is work happening with 1547.8 to kind of bring some method to the madness on that, but there's definitely still a few gaps from a distribution point of view. Also, what you find in distribution utilities is a wide variety of control capabilities. You see folks with no SCADA to maybe SCADA control out to the substation to full-blown distribution management systems, or distributed energy resource management systems, so DMS or DERMS. That's been fairly new to the industry. I know it appeared to have a little bit more traction at the show Distributech, if folks have attended that out in San Diego last month. So DMS systems and DERM systems are getting a lot more press, but that's really where you take a more model-based control approach and understand exactly what's happening down in the feeder network, can inform control decisions, and also understand just more situational awareness of what's happening in the network and how PV can contribute. But you see just this broad swath of capabilities within distribution utilities today. Another thing that you'll see is high penetration issues and congested grids. So a lot of utilities have taken somewhat kind of an umbrella policy approach where you may limit the implementation of PV onto a feeder to some percentage of the minimum load. I'll look at an example up in Ontario where original policy was to only allow PV penetration levels up to 20% of the minimum load, and minimum load is obviously a very small part of the overall peak load, so you end up with not really enabling a very high penetration level at that kind of percentage. So anyways, what are the things that we have to do in order to enable those higher penetration levels and make utilities a little bit more comfortable in terms of what these inverters can provide in terms of ancillary services? Inverter capabilities can be an alternative to traditional voltage management. So there's traditional voltage management comes in the form of cap banks, load tap changers, inline voltage regulators, etc. But there may be ways to leverage inverter technology to minimize cycles on those types of voltage regulation devices and really provide a service, not just solve the problem that PV delivers, but more be a solution to other problems that the utility is dealing with. And it's very true that I don't feel that UIC capabilities are being utilized to their full potential. So from a methods of DG control, we've touched on this. Centralized control is something which you typically see with transmission level applications or more advanced distribution utilities where they can make control decisions at their control room, and broadcast those control settings out to fleets of inverters. But in the distribution network, you're probably looking a little bit farther down the list where more coordinated control is needed, where they can perform studies in the back office, understand, what inverters should be doing at different times of the day from a reactive power or power factor point of view, so that they're not imposing additional voltage excursions, all the way down to autonomous control, where there may be, the ability for the inverter to monitor voltage out on the network and control itself accordingly in a very autonomous fashion. We're going to take a look at an example of coordinated control here in just a second with scheduled power factor, but I think that you hopefully should get from this that you really have to be extremely flexible in what the inverter control functions can offer, everything from kind of direct control all the way down to a highly configurable autonomous mode in the network the farther you go down. So from a volt-var control point of view, the utility's responsibility is to maintain system voltage for all customers under all conditions. But there's a big motivation by utilities to, do this in a more granular level if possible, because if you increase efficiency by maintaining voltage at a very thin, narrow deadband, then you can see improvements in your distribution support upstream. You can reduce losses. You can improve your overall margins of capacity in the network. So utilities have a vested interest in, performing more granular levels of voltage control if possible, if they have the assets at their disposal to do that. There's a wide variety of control techniques that they use. The location of devices on a feeder has a very large impact. So where a PV plant would be installed on a distribution network at the end, at the middle, at the head end, is going to have a very big influence on how the utility can leverage that for voltage control. You also have to take things into consideration such as feeder configuration. So if there's a fault or some other reason that the utility is motivated to reconfigure an area of the network, then that PV plant may be connected to a feeder with an entirely different load characteristic. So the inverter has to be somewhat reactive to being able to receive a different profile, different curve, different setting, set point, et cetera, to kind of evolve with constant changes in the distribution network due to outages, et cetera. And I think there's a real opportunity to leverage these distributed generation resources as assets. You can coordinate VAR contribution from inverter technologies and potentially sell that into a market. Now, I know that market doesn't necessarily exist, but I think technically there's a lot of opportunity for inverters to play that role. As a matter of fact, I was involved in some work in Denmark with wind and natural gas generation, and we were investigating technical feasibility of aggregating the output of those types of resources, controlling reactive power, and actually injecting VAR back onto the transmission network to improve overall efficiency. Now, the market didn't necessarily exist there, but the capability was proven. Therefore, it's kind of you build it and they will come. There's definitely an opportunity for the markets to catch up, I think, with what's technically capable with distributed generation resources in the network. So to get into one example, here we have a case study of scheduled power factor. And the situation here is that the photovoltaic plant actually represented a significant capacity on the particular feeder that it was installed. Some cases, 50 to 75%. So at the time, the utility didn't have the ability to directly communicate with the inverter, so they conducted studies and they wanted to be able to ask the inverter to do certain things at different times of the day, as well as different times of the year, because load profiles change based upon seasons and time of the year. So in this case, we implemented the ability for scheduling what power factor the inverter should be at based upon the time of the year and time of day. You'll see that schedule there on the left side of the screen. If you look in the bottom right, you'll actually see that we captured a transition between 2 months, where we went from kind of this 1 hour step to a 2 hour step. And what this really enables the utility to do is, instead of having to invest in a large amount of SCADA and DMS infrastructure, they can conduct some studies offline and really position the inverter such that it's providing the right service at the right time in this fashion. Here's another example where there were 30 500 kilowatt AE inverters installed in a 15 megawatt plant for PG&E. And you remember us talking a little bit earlier about low voltage ride-through. So traditionally, low voltage ride-through isn't a requirement in distribution level applications, but PG&E voluntarily implemented this feature to demonstrate the benefits. And I think it's pretty clear that as you see greater penetrations of these types of systems on the distribution network, the aggregate effect is such that you're going to have to, investigate these types of controls capabilities to really absorb these higher penetrations of DG on the distribution network. So here's an example chart that was pulled off of the SEL relay at the head end of that substation at that plant. So you'll notice that there was a voltage excursion on two phases, the A and B phase. I think it was an adjacent system or adjacent feeder fault. So it was cleared after 7 cycles, but obviously if it's going to be a fault that can be cleared quickly, and there's a significant amount of generation being provided by this plant, then PG&E would want to see this plant stay online, if at all possible. So this just represents a 50% sag event where the low voltage ride-through was successful. So then we ask, how is advanced energy addressing these challenges? So we've talked about the minimum ante of UIC functions that are required that, I guess at a minimum level. And that's something that we're offering in our solutions, as well as the scheduling and closed loop control that we've talked a little bit about. We're also focusing on partnerships and really trying to stick to our core competencies, but participating in a lot of forward-thinking industry activities. So we've partnered with other industry leaders through the CGIS. It's a DOE-funded activity that's been going on for 4 years and still continuing to go. There's a wide variety of activities going on with synchrophase anti-islanding detection, leveraging wide area data to make better control decisions, and a variety of the advanced functions that EPRI is working on. And just to give some examples, volt var control, looking at the frequency on the grid and controlling your active power output, looking at voltage on the grid and controlling your active power output. So there's a number of focuses in that R&D effort. We also have a relationship with Schweitzer to help us solve some of the issues around closed loop control at the at kind of a plant level. And then one other thing that we're doing is that we're investigating and adding kVA headroom over our rated kilowatt capacity. And what that allows for is the ability to operate at a wider power factor range without really sacrificing energy harvest. Power factor control is becoming much more predominant, and from an energy harvest point of view, we don't want any sacrifices to be there. So that's definitely an area that we're investing in as well. So to wrap up, I think that it's pretty clear that grid parity is not the holy grail that we expected. It's very clear that we're going to, as an industry, have to look at how integration can be conducted more seamlessly into the overall power system management of the network. And I think that overall, utilities will continue to constrain growth, and there's just going to be issues until a lot of those integration challenges are overcome. It appears that transmission level installations are taking on the look and feel of traditional generation assets and expected to perform as such. And then in the distribution level, there's just a wide variety of situations and circumstances you have to deal with. I mean, the infrastructure was designed to serve load, not support significant amounts of distributed generation in the network. And then you see a wide variety of control solutions that utilities have implemented to limit the amount they can access some of those functions, but inverters still should have the flexible capability to provide services on the distribution network regardless of the infrastructure that the particular utility has. And it's great to see EPRI and the activities around 1547.8 really trying to bring a method to the madness around distribution level PV applications. So I think I'll wrap with that. I have a final slide here that I'm trying to take control of. If someone else wants to move on to the next slide. Yep, so here's my contact information if there's follow-up after the webinar. And we also have some links there at the bottom of the page. I think this webinar is going to be distributed, so you can go find out a little bit more about us, as well as the LVRT case study that I talked about today. So really appreciate your time, and I'll hand it back over to Kathy.
Okay, thank you so much, Jeff. That was great information, much appreciated. And now we'll be hearing from Joe Brotherton. He is the Manager of Technical Services at Swinerton Renewable Energy. Joe has a broad background in sales and operations management. His responsibilities have included marketing, lead generation, sales, contract negotiations, operations, asset management, and service contract execution. Joe's experience in the solar industry involves operations and maintenance agreements for over 300 megawatts of PV facilities. Some of Joe's notable projects span from recurrent energy projects in California to Colorado State University to solar on the Staples Center in LA. He holds a Bachelor of Science in Business Management from the University of Phoenix. So thanks again so much for being with us, Joe, and please go ahead when you're ready.
Sure, thank you. And Jeff, I think his presentation did a great job of going through the technical aspects of what we as an EPC see in the market, and the multiple decisions that need to take place in terms of technology as it relates to utility control, technology control, and how we comply with, the various requirements of interconnection agreements, PPAs that the different utilities may have. Some quick background on Swinerton Renewable Energy. It's a division within Swinerton Incorporated. We are celebrating our 125th year anniversary this year. Typically a general contractor, about a $1.5 billion corporation, with the renewable energy division starting in 2008. We've been the EPC on a number of large utility scale projects in California, other places in the Southwest, and Nevada. So our view is really just an EPC, how we go through a selection and implementation process based on inverter technology, with the varying differences in the utilities we deal with. We look at multiple things. And the first piece of that is really the building block. We view the inverter as the brains of our site. So in making decisions from a construction standpoint, it's trying to decide which inverter technology gives us the most benefit in both our design and bidding projects. We've looked at all different technologies, string inverters, central inverters. Do we have an integrated power station? Do we build in certain blocks to take advantage of what these different utility scale inverters can offer in the control SCADA realm of what we do? Our first decision is really from a construction standpoint, looking at the power station versus stick building opportunities. A number of things go into our decision, the first of which is just the ease of installation. We deal with many types of agreements from different labor forces, different requirements of developers. So we look for the opportunity to partner with an inverter manufacturer that can help us make it easy to install. In some cases, we have poured concrete pads and we build up an inverter block ourselves. And in other cases, we've partnered with inverter manufacturers and other contract manufacturers to have a skid or power station arrive on site where it's as close to plug and play as we can possibly have. The other thing from a building standpoint we'll look at is QA/QC. We've standardized on a group of inverter manufacturers, where we feel it offers us as the contractor with long-term warranties and O&M requirements on these projects. We've partnered with people who take the same approach to quality and QA/QC that we do, and that helps us minimize the long-term risk, both from a performance and a maintenance standpoint. So all these things go into our decision process early on before we even get into the nuts and bolts of what this technology has to do. Once we get into that phase, the items we look for, I've listed a few here, and what we've seen in the market over just the last 2 years is inverter size, or the building block, really start moving in a different direction. Central inverters, if you go 3-4 years back, you had 250 kW, 333 kW type inverters. A 500 kW inverter was introduced. We can build off of that in a pretty simple block. And now, as we see the inverter sizes growing up to 1.5 megawatts, and in a single unit, it's kind of changed our way of how we build out our projects. Looking at DC to AC ratios, like Jeff mentioned, there is a strong push by EPCs to increase that as much as we can. When we look at different requirements coming from whether it be developers or the utilities themselves, we look at the technology having the capabilities of doing some monitoring or SCADA-related data flow further out into the field, whether it be DC inputs, combiner boxes. We even have string level monitoring on some of our projects. That's an option we look at. And then for many new inverters that are coming, we're seeing a trend to go into a modular approach where you have inverters being built with multiple engine components, and they're differentiating themselves by taking a modular approach where one module may go out, but you have a 1.5 megawatt inverter, and maybe you lose 250 kW chunk of that inverter and not the entire inverter. So we're seeing that being a big push, especially in the larger scale projects. And then finally, looking at compatibility with some of our other components as we procure just about every component on the site. We look at the ease of installation, not just for ourselves, but how we partner with our transformer vendors, with our switchgear vendors, how it conforms to the SCADA system that is being used on the site. So all those pieces go into our decision-making process as the EPC when looking at just bidding a job. From a control standpoint, I think Jeff hit the nail on the head. This is the part that we're seeing more and more, and while it's a simple slide with 3 bullet points, it's a month, 2-month long conversation with the parties involved to determine what is it we are really looking for, how far into the field do we have to go to meet these requirements. The inverter seems to offer us the most beneficial point of doing a lot of the control, and we see many of these operations being built into inverter topologies now. Dealing with a number of utilities, we see the requirements varying from your island type of installs, Hawaii, Puerto Rico, that are asking for very robust, almost creating a more stable grid environment, to utilities that really just want a plant to operate, and when something happens, the plant turns off, and then it's resolved. There isn't a whole lot of voltage control, power factor control being asked of us. As we see requirements, especially in California with CAL-ISO type of projects, the ability to curtail plants, control power factor, control voltage, have set ramp rates already in place for the site to function based on what the utility wants. It's becoming more and more important. We're building out a more and more robust SCADA system and needing a more and more robust inverter to help us along with that process. Again, as the EPC, it's not just install it, walk away. We're seeing a number of projects come with a requirement of maintaining some sort of criteria during the startup and commissioning phase, whether that be a 1 week, a 30-day, a 1 year type of test, meeting both control requirements, performance requirements, and then also looking long-term. A number of the EPC agreements we've seen recently have longer-term maintenance items being asked of the EPC. So maintenance programs ranging from 1 year to 10 years in some cases, maintaining the plant, especially the inverter, or like I said earlier, the brains of it. And what we go into in determining that is all of these technologies for us seem to be pretty new. So we look for runtime data. You know, and there's a number of case studies out there, various places for information on how utility scale inverters are operating today, comparing that with the performance criteria of the specific utility or the specific requirements of the interconnection agreement. And we have to evaluate that long-term cost and what it means to us being responsible for both performance and maintenance, and then the long-term cost to our client, who is ultimately the person holding this power purchase agreement and looking at the long-term ramifications of meeting or not meeting the different requirements. What I did for an EPC view, it's a pretty simple approach, we think, in terms of doing this. There are a number of inverter manufacturers, but we see specific inverter manufacturers starting to deal more directly with utilities, which gives us confidence in those products. I picked 2 sites, one of which was a late 2011 plant startup with the utility that did not have a whole lot of requirements. It's a inverter-based monitoring system where we saw a number of QA/QC issues come up on everything but the inverter, and it helped, you know, start to frame up discussions with the integration of a medium voltage transformer or switchgear with that inverter technology. It helped create what became more and almost a standard, robust startup and commissioning process that included different testing, whether it be as simple as opening a breaker, a command from the utility, all the way to actual curtailment, set point testing, cal ISO point-to-point testing. We've now grown in just the last 18 months into a full grid operator. That's really what we're trying to build here. Our 30 megawatt site varied. It's for the same utility, but seeing the change in the utility, going to a DC monitoring solution. They want as much data as they can. That particular site was a single-axis tracker site, where now we have utilities asking us to also receive tracker points that are available, position, angle, alarms from trackers, because they use that to also help with their forecasting, their grid operation, and then on that case, really building a robust SCADA system in where the utility has control. And we set up a number of different mechanisms through a plant controller setup like Jeff described, where the utility can control things like power factor and curtailment, ramp rates. It's no longer looking at the inverter level for us. We're now looking at controlling our sites at the point of interconnect, while the inverters make up a huge piece of that ability. We're now having discussions with utilities to go even more beyond that, and there's a real integration of all parties, you know, inverter manufacturer, EPC, and the utility, to have a clear understanding of what can and cannot happen. You know, looking down the road, we are seeing weather forecasting come into play on a number of sites, especially in those unstable grid environments, like I mentioned before. And the evolution is going to continue, you know, over the next couple of years as more and more renewable energy plants come online, and the utilities are going to press, you know, unfortunately or fortunately, it's going to be pressed to that inverter manufacturer to do a whole lot of what is really happening. So for us, from the EPC point of view, just kind of summing everything up, you know, it's been great to partner with companies like Advanced Energy and a few other inverter manufacturers that have really continued the R&D that is needed to continue to build specifically PV projects, and we're happy to be a leading EPC in that market, but we could only do it with partners that continue to fight the same battles that we do and really bring the technical piece or technical aspect to us. Short and sweet, that's what I have. And I guess we can open it up to some questions.
Absolutely, Joe. Thank you so much. That was excellent. We appreciate it. So yes, I'm sure after all the information, the audience does have some questions, so we'll begin asking those. Remember, you can still submit questions at any time in your GoToMeeting panel on your right in that box there. So we'll start off with Jeff, because we haven't heard from him for a little while here. Jeff, someone's wondering what lessons, if any, can we learn from Germany or other markets with higher PV capacities?
Yeah, I mean, I think that there's definitely a lot that can be learned. I mean, they've been facing high penetrations of photovoltaics in Germany for quite some time. Actually, a lot of my experience stems from wind integration in places like Denmark. And they're certainly at an inflection point where they have to become, wind in general has to become a better citizen on the grid and aggregate to provide a wide variety of services that can enable them to manage their overall transmission network much better. And I think that there's policies that have been implemented, standards that have been implemented that we can look at that really kind of point towards where I think our policy should be heading. So absolutely. I mean, I can't speak to too many specifics. My experience here with Advanced Energy is relatively short with a 4 months tenure. But I mean, I think that we can all look at how the market is evolving over in Europe and see that as where we're headed.
All right. Joe, someone's wondering, what is stick building? They are not familiar with that term and heard you mention it.
Sure. Well, the way we define stick building is going to dig a hole, pour concrete, bring the conduit in ourselves, land the inverters, land the switchgear, land the transformers all on one pad ourselves, versus going through inverter manufacturers where they deliver a fully integrated solution. So one skid that shows up that's already pre-packaged. That's just one piece that goes into our decision-making process, and really it comes down to how easy is it to install an inverter. That plays a big role in us going one way or the other.
All right, and this next question could be for both of you, actually, so feel free to chime in. What states in the U.S. do you draw data and experiences from? Is Pennsylvania in that mix specifically?
Hey, Kathy, could you repeat that question again? I'm sorry.
Sure. What states in the U.S. do you draw your data and experiences from? And specifically, they're wondering if Pennsylvania is in that mix.
Joe, you want to take a first step?
Yeah, sure. Our answer is pretty easy. The first answer is no. We have not done anything in Pennsylvania. The states we've dealt with are Oregon, California, Nevada, Arizona, New Jersey, Indiana, and then we also work in the Ontario province with Hydro One.
Yeah, and then from the advanced energy side, I mean, we've got a pretty broad deployment throughout the states. So I mean, I think it's safe to say that we pull from a lot of experiences. I know that we do have projects in Pennsylvania, but the specifics of those I'd have to do some research and get back with you if you want to ask me anything offline.
All right. This next one will actually be for Jeff as well. This person is wondering if you can share some experience about challenges faced with utilities and interconnection, maybe just briefly.
Yeah, I mean, some of the brief examples you could look at in distribution-connected applications. I mean, there may be a no backfeed interconnect requirement for a large commercial site, and in those cases, we partnered with other key, industry offerings to develop controls and closed-loop systems to prevent active power backfeed onto the network. So that's kind of where I get back to, really having the ability to have a flexible controls infrastructure, both with the basic inverter functions, but the ability to wrap a plant-level controller around it to enable some of those more challenging interconnect requirements. So, I mean, that's kind of a distribution level example. I'm not sure if that's exactly where the question was headed, but and there again, we can obviously get more details and talk offline if that's an area of interest for you.
All right. I think this could probably be for either one, but feel free to chime in. This person says they like the scheduling of the power factor, but they're wondering what is the impact of weather on maintaining that schedule, and what happens if your inverter can't meet the goal due to overcast or rainy conditions.
Kathy, you cut out in the last part of your question. Could you?
Oh, okay, that's okay. Yeah, they're wondering what's the impact of weather on maintaining the scheduling of the power factor. What happens if the inverter can't meet the goal due to overcast or rainy conditions?
So the interesting thing and kind of the advantage of utilizing power factor is that power factor really is your ratio of active power to apparent power. So it kind of scales based upon how much power you're producing at any given time. So if the question was more related to solar production changes based upon the amount of generation that you're doing, I mean, it does absorb that somewhat with the scaling. As far as seasonal changes, in terms of overall load patterns, I mean, that's, whenever the utility does the analysis to figure out, during this time of the year, the load's going to be approximately this. I mean, averages are really kind of taken into consideration, not necessarily day by day specific weather conditions. So I hope that answered the question. Just depends on if you're talking about load or solar generation as to what you really have to look at. Sure.
Jeff, what are some barriers to higher penetration of DG?
And we touched on this a little bit earlier, but I think that a lot of the ancillary services that can be provided by photovoltaic inverters have yet to be monetized. I mean, I think the same thing exists within distribution utilities as well. Distribution utilities are paid to deliver kilowatt hours. Inverters are paid to, generate kilowatt hours worth of energy. The markets for this voltage control, power factor control, curtailment, downrate, at least at a distribution level, have never been monetized. I think we're now being able to demonstrate those capabilities, but until the markets are really in place to enable capturing that value, I think it's going to be a little bit of a chicken and egg in terms of getting over some of the challenges of these implementations and integration challenges. But that's kind of what I see as a key barrier to summarize is the markets don't quite exist yet for those ancillary services down in the distribution network.
All right, I believe this may be for Joe. What kind of problems have you seen with the integration of SCADA systems in the utility? How is this done from one utility to the next?
Yeah, do we have about another hour to talk about that? That's really the part that I think everyone is still learning. Our approach has been we've brought SCADA in-house and tried to bring in experts who understand from a generation side, and then the generation as in the PV plant side, and then the utility side. And finding those people isn't the easiest thing because at the end of the day, what we find is utilities want everything, and they want to know their grid is protected, and they don't know how to do that, so they just expect that we're going to set it up that way. So the main challenges are asking for things within a time frame that is, in our opinion, at times not possible. So things to react within milliseconds and make a huge change while inverter technology is coming up to speed on these types of things, that's been the real challenge, the timing that they want a lot of these changes to happen in. And then I think the question was asked earlier, and I think Jeff's right on the forecasting or what-if scenarios with regard to weather. We're seeing utilities now want to build in, performance or reactions of the PV plant based on weather. So tying in weather forecasting into the SCADA system is the new challenge for us in how we do that. When it comes to just sharing data or giving utilities control, we think that obstacle's been overcome. There are a number of sites. Jeff used it as one of his case studies where utility control is a huge factor, and a year ago that's what people were trying to figure out, and I think they figured out the basic control functionality, and now it's going to a more advanced level that there's a lot more to deal with. The other thing from the EPC point of view is our client usually isn't the utility. It's a developer who's in the middle and still wants everything based on their PPA, which may not easily coincide with what the utility wants. So we as the EPC are playing the balancing act between the utility and the developer, but as the requests grow, the technology is going to have to keep up.
Okay. This may be for Jeff, I think. For utility scale installations greater than 10 megawatts, will UL 1741 or IEE 1547 be a requirement for the inverter, or is that only on the distribution level?
Excuse me, go ahead. Was there something else?
I'm sorry, did you hear the question, Jeff?
Oh, yeah, I did. Sorry.
Okay.
Just heard you speaking up. Yeah, so I guess we're speaking about, the application of UL at different, plant sizes. I think it somewhat varies from utility to utility. Behind the utility's fence, if you will, the utility has a lot of latitude in terms of how it wants to utilize either the standards that are set forth in 1547 or 1741 versus kind of leveraging the LVRT. I don't know that it's necessarily a size of project question. I think it's more related to who's developing it and what's the relationship to the utility that's purchasing the power. So I would kind of leave it at that. But there again, if there's more information that's wanted, I can obviously do a little research and get back.
Yeah, and I would echo what Jeff just said. We're not seeing it based on size. We have a 5 megawatt site with a non-UL listed inverter. So it just depends on what the requirements are, what the utility is really looking for. We just recently saw a request that's a 2.5 megawatt site, and UL 1741 isn't a requirement.
Okay, perfect. Jeff, what are your typical DC-AC ratios that you've experienced with your inverters, and through what means do you expect for that to change in the future?
Well, I think that it's safe to say that DC to AC ratios continue to rise, just given the evolution of panel prices. AE's inverters support a pretty wide range of DC to AC ratios, upwards of 1.75 on some of our inverter technologies, and we've even, I think, permitted up to 2.0, and we obviously had to do a review on the overall design. That was kind of a special case. But in general, you're going to see 1.2, 1.3, kind of in that range. But we've seen things quite a bit larger than that.
Okay. Maybe this would be for Joe. What leads to, or can you just discuss the maintenance associated with central inverters versus string inverters, maybe how it differs?
Sure. What we see on the string inverter side is almost the unplug, plug in the new one type of approach. So while there's annual requirements, if there is a failure of some sort, we're more just replacing the inverter than fixing it. On the central inverter side of things, there's, from every manufacturer, they have their recommended maintenance, but it's more fixed in place rather than look at a replacement type of model. One of the things we view and we build into our selection criteria is we don't want our client to ever have to plan on replacing central inverters either. So this notion of, at year 11 we're replacing every inverter, we don't like that approach. We like that central inverters are almost like your car. You do oil changes, you have major tune-ups that are required, and ideally if you're doing everything you're supposed to be doing, they run for as long as we need them to, or at least within the design of the inverter we select.
Okay, going back to DC-AC loading ratio, someone else is wondering, Jeff, what's the effect of high DC-AC loading ratio on inverter life?
So that's something which I think it really just depends on the particular technology that you're using within the inverter. It's not an area that I'm extremely versed in, so I may have to punt a little bit on that question. But there again, if there's a request for more info, definitely follow up with me on the side. So long story short, I think it depends.
Okay. All right. Well, I think that's all we have time for here. That was a great discussion. Jeff and Joe, thank you so much for all your feedback, and thank you to the audience for all your great questions. Again, thank you, Joe and Jeff, for being here to share your expertise with us, and Advanced Energy for sponsoring this webinar. So also thanks to everyone in our audience for listening. I hope you enjoyed the presentation. You had great questions. And please do join us in a future Solar Power World webinar. There are lots more to come. Thank you so much, everyone.